idea is that I want to give a enough background before we do TensorFlow next week. So I don't want to steal his thunder. So I will not talk about. So I think I'll leave a little bit earlier than that TensorFlow also. So I think I will go up to maybe MapReduce and stop there. And I think then he will start about MapReduce. He'll talk about Regal Giraffe, another parallelization paradigm. And obviously then he'll talk about parameter servers and then go on to TensorFlow. So yeah, so that is the current plan. All right, so let's start. So the first question, we'll start with the question for everyone. So when you're building a software, right? So what are some of the things that you want, you would like to have? What are some of the properties you would like to have in a software? So this is going to be an interactive session, okay? Otherwise it will be very boring after 2 o'clock on a Sunday. So what do you all say? What properties should softwares generally have? Okay, it should be scalable. Okay, that's one good property. Modular. Okay, another nice property. Say that again.
Software user, so it has to be more user friendly.
It has to be user friendly. Absolutely. Okay. Okay, it should be easily updatable. Okay. I think one of you, if you sit there somewhere, you can be the relay person. Okay. It should have. So what do you mean by quality there?
It's like not everywhere. Like if it is there in production or that kind of environment, it should follow some standard like MISRA standard.
Right. I mean, so what do you want with that? What is the end goal? Meaning, what kind of quality do you want?
I mean, like following quality means it will not produce much bug. Kind of like.
So it should be bug free, right? That is the property you want. Okay. It should be bug free. Okay. It should be platform independent. Okay.
There should be arrangement for proper logs so that it's easy to debug and trace problems later on.
Okay, that's there should be some amount of logging capability as well. Okay, what else? Okay, so then I will continue. So these are some of the things I had noted down. Things like modularity, correctness, maintainability. There should be security, right? Another very important thing of late. Functionality. You want all functionality that is there. Robustness, and then on the other side you also want user friendliness. Simplicity, extensibility. Right? You don't want to write a software that cannot be extended further on. Right? Reliability and scalability. So some of the properties that we could think of. You could add any more here, right? So the question is really why do we need performance, right? We need performance for one reason of why we need performance is we can use performance to pay for a lot of other things, right? So meaning if you want user friendliness and if and in some sense also performance is correlated with user friendliness, right? If your UI is really very slow, then no user is going to use it, right? And the other thing also is that performance is like money because if all your modules are written very efficiently, if you want to add a new feature, that's easy possible. If you want to add more security, that's also easily possible. So in some sense, it's like currency, right? You have performance, that means you can do a lot more other things with the software, which will be very amazing to have. And also it tells us what is feasible and what would not be feasible. Right? So because of all these reasons, performance is very critical in any software that we develop. And obviously speed is fun as well. Right? So let's start with the big O notation. How many of you are familiar with big O notation here? Okay, some of you have a picture. Okay, so I'll keep going. If you have questions, if you have doubts, we'll stop there. So first question, right? How fast can you multiply a 1000 by 1000 matrix? Anyone? No, in terms. Let's talk of first in terms of big O. I mean, what is a naive algorithm for that? Can we do it n square? Okay, I've heard two answers, n cube and n square.
I know it's between the two because of one method.
What is that? You know it is between the two.
N power 2.43. I'm not sure.
Okay, okay. So this n power 2.43. Okay, interesting. What is that? Less than that as well. Okay, slightly less than that. Okay. Any other big own notation values you want to give? Okay. So what is the do you know algorithm to which they can do O of n square? Anyone? Anyone? For matrix multiplication, how fast can you do?
Then won't reduce it, but it will be like doing a lot of matrix multiplications parallelly, or
No, we are talking about just a single sequential case, right? So okay, so you would at least do O of n square. Do you all agree? Do we agree on that? Why is that the case? So at the very minimum, you need to at least look at all the elements, right? If you cannot look at the elements itself, how can you do computation? Okay, so at least you need O of n square. But as of today, we don't know any algorithm to do that. There was a recent paper where they have do conjectures about it could be potential. This is the lower bound, but there is no algorithm that we know of that can do this. Okay? The best, as far as I know, is O raised to 2 power p7 or so. Okay, that is the Coppersmith Vinograd, I think. And so let's take the simplest algorithm, right? O of n cube. So how much time will that take on our modern day processor? What is that? 2 seconds. Okay, how did you get that? Can you tell us the what was your thought process? No, let's just ballpark figure. That's not. I don't need the exact number, right? Okay, so 1 gigahertz, 10 gigahertz you're saying, okay. So, and how many instructions is that? So 1000 times 1000, and so n cube is what? 10 power 9, okay. What is that? What is that? Yes, we are multiplying 2,000 cross 1,000 matrices. What is that? No, oh, sorry, okay. Yeah, you were saying. Yeah, it is a 1000 cross 1000 matrix. Okay. Right, you're multiplying this times another y to get a third one, which is of the size. So let's just go through that once, right? So 1000, and this gives a 1000 by 1000. Are we all on the same page? Okay. So now you'll go through. Essentially you will take, right, and you keep on doing that, right? So how much? So that's essentially like a 3 for loop, right? So that sort of is like a O of n cube. I mean, that is the back of the hand calculation, right? Do we agree? So that is 1000 times 1000 times 1000, right? So 110 raised to 9, which essentially is how much time does that take? So 10 raised to 9 operations approximately. Current day processors can do, let's say, 10 raised to 1 billion operations a second, as you said, 10 raised to 9. So that means how much time does it take? About a second. Okay. Are we all on the same page? Okay. All right. So in that case, now So which is it's not exactly correct because you can do a 3.4 gigahertz processor, for example. So in that case, how big of a matrix can we multiply in 1 second? Okay, so it's not something slightly bigger, right? Doesn't matter. I just want to get you guys a feeling of what you're talking about here, right? So now let's come back and look at this figure here, on the left. So as you can see, this is the plot of different Pigo. So as you can see here, this is of n, that's linear time, and you can see here of n log n square, etc. Right? So let's say, for example, if I had, so I'll come back to that. So okay, I'll keep moving here in that case. I'll give another example in a moment. So as you can see here, so the big O really gives us a ballpark idea of how much time it will take to compute something, irrespective of the architecture. So in that sense, it's very helpful for us in order to use it. And we'll see one or two more examples as we go forward. And just for sake of knowing these keywords, when something is log number of the size of input, we say that's logarithmic. Otherwise, it's below that is constant, and something less than n, order of n, that is order of n is linear. Anything below that is sublinear, and then you have n log n, and then you have quadratic, which is n square, exponential and factorial, etc. Right? So for example, if I have a input of, let's take another example. Let's take I have an input of 100 things. Okay, I mean input of size 100. What kind of an algorithm can I do in 1 second? Meaning, so of n square or of n cube, up to what can I do in 1 second? So size is 100. Let's just use 1 gigahertz for simplicity. Right. Okay. So even with 100, right? Even anything more than n raised to 4, we are pretty screwed, right? So we want to make sure that it is less than n cube or something. So usually a good algorithm is something in this n square or n log n, for example. Okay. Anything that is more than that is usually not a good idea. But again, it depends on the size of your input and how usually your inputs are. Right? So that's just to give you an idea before we started. So maybe before I jump in there, how can you make your program faster? What are 2 ways of doing that? Okay. Okay. What are 2 big, thought process wise, what are 2 big things you can do to make it faster? Parallelization, okay. Okay, I mean in the bigger picture, right? Parallelization, memory all come under this one umbrella term, I would say. So one is algorithmically, right? Which is you can say but from algorithm, right? Other is when if you are mentioning which is the architecturally. So either you can have better algorithms to do it more cleverly, right? Which is using, and obviously using algorithmic analysis to improve it. Or secondly, what you can do is having better architectures, right? And for example, one example of such, improving better architecture is using Moore's law, for example, which allowed us, it's not necessarily better architecture, but just the fact that we could pack more and more transistors onto the same area, every, at least for last 30 years or so, we could do that. Every year we could double that almost, right? So not exactly double, I think it takes about 18 months to double, but that's sort of what the law says. So now, so that is one thing that we could keep doing, right? Earlier we had other limitations like, we needed, for process were not much faster, but today they've become much faster than let's say what we had in 90s or 80s, right? And memory has become much cheaper, right? That's other major improvement that has happened. But still theoretically there are, on a single processor we have certain kind of limitations, right? One is there's a limit to miniaturization, right? We'll talk about that in some time, which is how far can you make your chips? How smaller can you make them? Next is there is a speed of light. The amount of time. So you have a bunch of components, each of which takes some input and does some processing and gives out. So usually it takes there's some delay before which you can actually write out after you do the operation. That is non-zero. And other thing also is that the speed of light, which is a bound on how fast can you communicate. So there are two things there. And finally, the other thing is memory transfer, right? How much memory can you get in? So these are three things that definitely are, from a single processor perspective, at least theoretically itself, there are three different limitations. Now let's come back to our the first case of better algorithms, right? So the way the talk is structured is that first I'll talk about few examples of better algorithms, and then I'll talk about architecture side of things. Okay? And with that, we'll wrap up today. So the first one, which is better algorithms. So linear search versus binary search. So how many of you know what binary search is? Okay, almost everyone knows. Anyone who doesn't know binary search? Do I need to? Maybe I can just give one example. Okay, sure. So the idea of binary search is very simple. You've got a bunch of things. Let's say, let's say a few numbers. 1, 8, 4, 3, 2, and let's say 7. Right? And now I'm going to find the maximum number here. So, or actually, I need to sort it. Or I have to go ahead and then sort it. So let's say 6, 5, 7. I don't know the right numbers. So let's say, for example, I want to find a particular value, right? So instead of maximum, I'll do a particular value I want to find. So if I want to find where is 5, for example, right? So one way of doing to find a particular value, do find how fast can I do that, right? So one way of doing that is what is called linear search, which is you just walk through one after the other and you see how much time it takes, right? And how much time will that take? People who don't know, people who know, you can keep quiet for a second. How much time will that take in big O notation? Order of n, right? The size of, you have to go through every one of them to know whether that's right. And if it is the search idea of binary search is that if it is sorted, okay, you cannot do if it's not sorted. If it is sorted, what you do is you go look at the middle and see if you have found what you wanted. If you haven't found, then you only search in that side of it. If it's less than, what you're looking for is greater than, then you search on one side or otherwise another side and keep recursing. So that essentially gives us a guarantee that it can be log of n, right? Now how just to get our thought process in the same line here. So O of n versus O of log n. How big of a thing can you do with O of n? How big of now a set can you do binary search on in 1 second? Okay, and linear? Okay. So linear is 10 to the power 9, right? So you can do up to 1 billion items. You can search through them and find out what is the one that you're looking for, right? So if you have more than 1 billion, if you have 1 trillion things to look at, then what should you do? So how much further can binary search go? Ten power. So you see that now, how much more powerful it becomes, right? So that is why you should always worry about some of these algorithmic ideas, right? And I'll give the kicker at the end probably. So we'll come back to our thing here. So that's just to give an idea of why those things matter, right? So next one, let's go to our matrix multiplication, right? So we said that it takes naive algorithm takes O of n cube, right? So and the way to do that, one way of doing that is what is called the block-based matrix multiplication, wherein you divide the matrix into 4 parts, and then you can do multiplication of them, right? So for example, here I can say R equal to AE plus B times G, right? Do you all agree? Okay. Similarly for S and T and U, okay. Is that clear to everyone? If you have questions, you can ask now, because I'm going to use this for the next slide also. Is it clear? Okay. So how many multiplications do we have here? In this equation, those four R, S, T, and U. How many equations do we? How many multiplications do we have? 8 multiplications. Oh, I think I've written the answer there. Like that. And how many additions? 4. Right. So now that, and so essentially what you're doing is 8 multiplications of n by 2 and n by 2 matrices, right? And 8 additions of n by 2 and n by 2 matrices, right? So that actually you can write in your what's the word I'm looking for? The recurrence formula. Recurrence formula is 8 times t of n by 2 plus theta of n square, right? Which when you solve you get n cube. I think I won't go into details of that for now. But if you haven't understood this, go back and I'll say watch lecture number 2 or 3 MIT algorithm 6046J. I think. So I will keep that there and keep moving. So now what? So the naive algorithm we described about now, right? So what this person called Strassen in 1969, what he did was that he changed that multiplications to 7 of them, and the additions, it increased by quite a bit, right? But that actually turns out that algorithm is much more efficient, okay? And when you do the master method and you solve it, someone is there. Just tell. Come on. So then they do this recurrence, okay? So if you want to know how the recurrence works, maybe we'll try to do that during the break period, break time. Break time. That way, we can go through that. Okay. But now, for now, you believe me that you get this. It finally comes out to 2.8, 2.80. Now, can someone say what is the effect of that going from n cube to order of 2 power 80? So n cube we said, right, we can do up to a 1000 by 1000 matrix. Okay. With this algorithm, how much can we do? You can just run your do some. Somebody got the numbers? No, this is an active session. It won't be passive. So if you're not doing, I'll do it. How much is it? Someone got it? No, approximately. We don't know the exact number. How much does it increase to? Where is my calculator? What is that? Which is 10 power 3.2. Okay, about 1500 or so, right? So that itself we can see, even for that 1 second, we're getting a decent, reasonable improvement. Okay, so imagine if you can have a slightly better algorithm, right? Okay, so and the good thing about this algorithm is that even it is actually practically possible. Okay, it actually gives you. It's not just theoretically you have this result. It actually is practically useful also. There are some conditions, there's some gotchas, but in general that is useful. So next, the other one, the current bound on matrix multiplication is this algorithm by Coppersmith and Winograd, which is the one I was saying, 2.37, right? And that actually unfortunately is not very practical. And also recently there was this paper where they gave 2 conjectures which could lead to the optimal algorithm, the of n square algorithm. Okay. With that, I'll keep moving. Okay, so now till now what we are talking about is how do we make algorithms better for a sequential computer, right? And we were just playing around to see what effects they have and how can you do back of the envelope calculation to get an idea of how much faster things can get. Now let's go and talk about parallel algorithms, right? So now, can someone tell me this? So, and to this question, whether you can try to answer this question. So I have an algorithm A, okay, and I have algorithm B. Algorithm A, it takes 1 minute to compute on my processor, and algorithm B takes 1.2 minutes on my computer. Now I want to see which one should I use for running on my cluster of 10 computers, right? How much faster can I get each of them? Any thoughts on that? So one takes 1 minute, another takes 1.2 minutes, okay? Or to make it simple, I'll say 60 seconds and let's say 70 seconds, okay? And I have 10 core, 10 processor cluster, and if I do it on that, I want to know how much time it will take. Right, it depends on the algorithm, absolutely. Sure, I mean, theoretically, what is the bound you can give? 6 seconds, and is that correct? Is that the best we can get? Can we get better than that? Can we get less than 6? So what you said now is linear speed up, right? It's increasing your linear scale speed up. So it is increasing as the number of processors you increase, right? But my question is, can you get super linear speed up? Okay. We might get, okay. Some.
Doesn't have any dependency with other segments.
Uh-huh.
It can execute parallelly without waiting for attention.
But dependency creates better results.
Uh-huh.
When you make it a super linear.
How could you get that?
Depends on the problem.
Okay. Anything else someone can think of? Actually, Google had did this. Distribute the data. Okay. Uh-huh. 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 But it will still be only 6 times. If you have 10 processors, it will be 1/10 of that time, right? It cannot be better than that. There has to be some.
If there's some dependency on the future, if the future instructions are dependent on earlier instructions, if you run them parallelly, then you can use the other processors, the output of other processors to be used to improve and get a better data.
Correct, but do you really think? I mean, because even then it can only get up to up to linear speed up. It cannot be beyond super speed up. I mean, it can be beyond linear speed up, right?
So, but if there's dependency in
So can you give an example?
I cannot
Okay. Okay. Think of it. Okay. There's something along the lines of what you are saying, but it's not the exact same thing. And there's an example of this. Google and all did this. So all of that only can give you up to linear speed up. I mean, linear speed up with certain star on what linear. I mean, what do you mean by linear based upon? So yes, what you are saying is sort of true, but it sort of kills the major point there. So one way to get that, okay, so it's usually unlikely. Okay, the only way usually one of the ways you see that, okay, is for example, earlier you had a single machine on which you only had, let's say 1 GB of RAM, right? But you needed 10 GB of storage, so you're hitting the disk. Okay, so now when you do it on multiple machines, what actually happens is on that huge machine of 1 GB each, you might have 10 GB of RAM. So everything is then actually you are doing a RAM access as opposed to a disk access. That can actually give you a speed up. Okay. So there are cases such this. I mean, so Google, when they were building, at some point they realized that what, if we add a few hundred more machines, or whatever the order of magnitude there, then actually we can put everything into RAM. Okay, in which case their user queries will reduce. What is that? Yes, there's a question about how much communication overhead you have. Okay, so you need to worry about those things. Absolutely. Okay. So anyway, so in general you don't get super linear speedup, but at best you could get super linear. Now one more question on that front, which is I gave you two algorithms, right? 60-second one, which takes 60 seconds on one computer, and second one 70. Can you necessarily say that the first algorithm would be faster when you parallelize than the second algorithm? What is that? It will depend upon the. No, let's forget the disk read now. Okay, that is the first case. Right now we are not worrying about disk read. Okay, so I've got two different algorithms A and B. Each takes. Right. It depends upon what of the. Right. So what I wanted to say here is that not necessarily your best parallelized algorithm need not be your best sequential algorithm. Okay, so that is the point I was trying to make there. So it depends really on the amount of what is called the critical path length of the algorithm. So, okay. So now, okay. So we have running time on one processor is if t of 1, and Tp is the running time on of p process, and T infinity is the critical path length, right? Can anyone know what critical path length is, or do you want to give a guess of what critical path length is? So let's try to, right, let's try to, I'm going to do on the board, you want to, okay. So, okay, I'm trying to create one on the fly now, let's see how far it goes. So let's say A1, okay, oh, okay, how about that? Okay, that won't work. Okay. If I do it here, that's fine. Okay, and let's say, or yeah, let's just do it this way. I'm still thinking on that. Okay, I'll come back and give an example of that. Okay, critical path length. So the gist of the idea essentially there is this, that it is that chain of series of tasks that you need to do that you cannot any further reduce. Okay, and that is what critical path length is. Okay, and so that, for example, if A dependent on B, that depend on C, which depend on D, I have to do them in that linear order of doing things. Correct. Yeah. So here you can actually understand what the critical path length is. Once you have a critical path length, you know that it cannot be any shorter than this, because for me to do this operation, this has to be done. For me to do this one, this has to be done. For me to do this one, this has to be done. So once you have the dependencies, then no matter whatever, how many other things you have to do, you cannot get any more efficient than this. Right? So that will be what your T infinity time would be. Right? If you had infinite number of processes, that's actually what it would be. In practically, it might be a different story, because it may not just be this, right? There's communication over and other things as well. So your T infinity practically and theoretically might be two different values. Okay. So now, so as we said, it is less than P. If your your speed up is less than P for P process, then it's supra, and if it's more than, it is super, right? And now our ideal thing is that we want to get linear speed up, right? As we increase the number of processes, we want to at least get as much as that this one is, but usually it's not the case. It is very hard to get that. Now the maximum parallelism, or that's the parallelism that a algorithm has, right, is actually nothing but T1 by T infinity, right? So if you take an algorithm and you compute the T1 to T infinity, that number what you get is essentially telling you that, okay, if I had let's say for example it is 70,000 for example, okay? So if I have 70,000 processors, after that anymore I scale up, it won't help me at all. At max, the improvement I can get is by a factor of 70,000 and not anymore. Okay. So this essentially is giving us, that is essentially by doing the critical path length analysis, it's telling us how much parallelism that particular implementation of that algorithm has. Does it make sense? Okay. And that we call parallelism. Okay. In a given algorithm. And what do we usually do now if you want to, and we can use schedulers to then start scheduling the tasks. Right? Now what is, anyway, everyone knows what difference between greedy and non-greedy is? Anyone who can tell me what greedy versus non-greedy? Choosing the best option available, okay. Something slightly more specific. At that specific point making a decision, okay, that is better. Someone can maybe give me an example or something of a greedy and non-greedy problem. Yeah, no, so you forget the process scheduling case, right? Just think of any other problem, any general algorithm. Right.
Actually, we can come with something much better that could reduce the processing speed by 5 seconds for 2%. Right?
No, so greedy is not about that. Okay, so greedy. So the question I'm asking here is, to be precise, mathematically, what is a greedy versus non?
That, let's say, given a circuit, we have taken action. So I have an action space. Now, given a state, I have to take an action. So the greedy would be actually looking for all of the actions and changing the action would be from which action I am taking.
Okay. Okay. So I'll give an example. Okay, just to make it clear, right? So imagine, let's say, we have it's very similar to what you all are saying, but I want to give an example to sort of showcase the differences, right? So imagine you have a bag, okay, and you have 10 items that you want to put into the bag, right? So my first problem is, I'm saying, okay, put in things into the bag such that my put in with the minimum number of items such that the value in the bag is more than certain amount. Okay, so I have got n number of items. Okay, 1 to n, and each of them has value v1 to vn, right? And I am saying out a bag, and I am saying put n items into this bag, such that it is of it is more than a certain threshold of value. Okay, so that is do you all agree? How can we solve this efficiently? So I am saying 1 to n, and I am saying with p of them, at least p value or more. Okay, I need to fill the bag, right? So I should have put stuff here such that it's more than p. How can we solve this problem? How do we do greedy? Okay, so we'll sort all of them by value, right? Pick the one with the maximum value, keep adding, right? Till we are more than p, right? Is that clear? Okay. Now let's say I change the problem. Okay. Now I say it has to be exactly p. Okay. Now will your greedy algorithm work? Why would the greedy algorithm not work? Correct. We are not looking at the global solution, right? Because in order for us to reach a particular p value, we need to backtrack from what that is in order to make sure that it actually will be effective. Right? So that's an example where greedy won't work. Right? So greedy is local decision making. Locally, whatever is optimum, you do that, and hopefully that will solve the problem effectively. Whereas non-greedy is where that's not possible. Right? Whereas in our case, for example, when a processor is scheduling tasks, right? You might not have all the context of how much time each task will take. Right? So you don't have a choice but to be greedy, in some sense. Right? You can do more things. Okay, you could probably have historical data of how much time different things take. You can take statistics on them and then do more intelligent ideas. Right? Okay, is that clear? All right. Okay, so now let's go for our favorite matrix multiplication. Now let's talk about how we could do this parallelly. Right? So, and what we do is, so the matrix now I'm saying, I'm dividing that into 4 pieces again, and this is my original matrix which I'm trying to multiply, and which I'm saying, is nothing but this, right? And to do that, what do? I have a matrix multiply which takes, it takes a matrix and keeps on doing a multiply operation. And I also have in between a temporary one. So, for example, A12, A12, and B21. So these two, I store them temporarily in a temporary variable t. Okay. Everything else I store into the matrix. So first time what I do, after I do this, it will be just this one and that one will be stored here. This one and that one will be stored in that corresponding one, etc. And I have a temporary matrix as well where I store it. Okay. That is my first parallel implementation. Is that clear? Questions? Okay. And then I have my equivalently. So I do that. Matrix multiply for all of those guys, and what do? And then I do the matrix add as well, then which does the addition, right? And this one actually you can see that the parallelism given by this particular algorithm is a factor of 10 raised to 7. Okay, so up to 10 raised to 7, I can actually use this particular algorithm to give me. I mean, it can be parallelized up to 10 raised to power 7. Now this is a theoretical guarantee. It's not really telling you about practically when you do with how far it will go, right? Is that clear? What that point here is? It's the inherent parallelism in that particular implementation of the algorithm. Oh, okay. So that actually we did the analysis, the critical path analysis for this particular one, and so yeah, I will suggest go and watch MIT lecture number 21, 6046. That's the course number. First is lecture 3 and this is lecture number 21. Okay. So you can they actually derive through that. Okay. It will take at least an hour. I think at least take 20 minutes or so for me to go through it. And I don't remember it off my head. Okay. Now the second one they do in that particular same course itself is now you already have the temporary variable, right? If you reduce space, for example, right? Now what do? So in that case, what happens is the amount of parallelism comes down, but you can remove the temporary variable. Okay. So always you're making, so the point I'm trying to make here is you're making a trade-off between how much parallelism the algorithm has and how much scalability you might have, etc. So there are always trade-offs you're making. Okay. Now yes, when you're implementing algorithm, it's unlikely that you're going to do a critical path analysis on the algorithm. But you should have these things in mind when you're making those choices, right? Oh, maybe I'm taking a hit here, and you could do quick back of the envelope calculation to give you an idea of how bad things could be. Okay. Oh, that one, no? Okay. So that is T1 by T infinity. That much. The algorithm could have that much. I'm not, so meaning what I'm saying is if I put it up to 10 raised to power 7 number of processors, it will give me linear speed up. After that, nothing is not any more helpful. Okay. Questions? Okay. So what we are really understanding here is, given an algorithm, many a time we can do two things, right? One is to make it more efficient, right? Which the first part we spoke about, right? How do we use that right data structures? How do we use right algorithm to implement the routine that you have, etc. That is the first and foremost thing. Okay. So just by using a O of n versus O of log n, you can have a huge speed up, right? Second is try when you have when you have parallelism available on your architecture, then try to utilize parallelism, for which you have to make sure the algorithm itself allows for that parallelism, right? Which is what we are talking about the second. Right? We saw examples of how we created a parallel implementation of the same algorithm, right? Where
as you said, if we go beyond 10 raised to 7, it will speed up further, right? So what will happen? Will it slow down or
it will remain the same then, right? Why is because your critical path of you have to do A, B, C, and D. Okay, so that will take you whatever that number that you get at 10 raised to 7. Okay, but beyond that, whatever you do, you still have to do that much things. So on a given single processor, you have to do these many things. So no matter more, what is that?
They can't be used.
Correct. They cannot be used. I mean, yeah. Yes. I mean, they cannot be used efficiently. They could be used, but at the end of the day, one processor will be there which will take this much time, right? Which means that everything else is still going to take that much time.
If the matrix size is smaller, let's say 100 by 100 or even smaller, then like
Correct. It's not necessary. This is a good algorithm also. Okay. Yeah, and usually there are always trade-offs. Okay. For small ones, you don't have this one. And again, this is not exactly how matrix multiplication is done. They do what is called, they do very small. They choose the right size of blocks in order to do matrix multiplication. So I think one of the better implementation is this one called FFTW, fastest Fourier transform in the West. It's called, which what they do is essentially they have those, they know at what level of blocks you have to do. And again, you know, the next thing, this is sort of connects to what I'm going to talk about next, is that it's not just a function of how much faster you can do. There are other things you have to worry about. Okay, for example, cache miss. Okay, if you have a huge block and you give it to your processor and you have a cache miss, then your performance take a big hit. Okay, so there are a lot of other things also you need to worry about. Currently, you're talking about a very theoretical model, but when practically you come to it, there are other things you need to worry about. Okay, all right. So let's talk about how processor interacts with your memory and how the system itself is just laid out, right?
One question from the audience, I mean the YouTube live audience. Is multi-threading example of parallelization?
Yes, multi-threading is an example of parallelization. We will talk about that in a moment. Okay, so now, so you have the CPU and you have your memory. So this is your memory bus. This is your, I think it's called IO bus. I forget what it's called. I think our hardware people should tell us. But yeah, so essentially these are very fast mechanisms to transfer data between them. And this is your bus, which your peripherals and everything else is connected to. Right? Now, and just for your knowledge sake, there are two different kinds of architectures. What's called as the von Neumann versus Harvard architectures, where von Neumann is the one where the memory unit. So the gist of the idea here being the Harvard one, where your input, your instruction data are set on completely different memories, whereas in von Neumann is just one single memory which you talk with. Okay. And algorithms have, I mean not algorithms, architectures have been they have been moving around a little bit as well. There are reasons why they do it the way. We'll talk about that. So now the big picture. Let's come back to the OS level, right? So what happens? You have a process which you want to execute. Now this process itself gets scheduled in order to be done on a particular processor, which is what your OS scheduler does. Now it gives that to the OS scheduler, and the OS scheduler gives that to the processor, which in turn has the job of running that particular process, right, or a thread. And now the thread itself is run by, this is where you're just running that thing, and the processor itself, the OS itself does context switching, right, which means it switches between each process based upon some sort of division of time, right, and priority and other parameters. Now at the same time, the processor also has some whole bunch of things. Okay, there are what are called, so you have your software threads that you usually use. Then there are also hardware threads, right? For example, your what is it called? The Intel's hyperthreading. So Intel's hyperthreading, for example, right? Where so the architecture itself can actually have threads that do context switching inside the processor. Now, so what happens? So when you give a task to be done, it goes through and it goes to your CPU, and it's a CPU is where your execution actually happens, right? But before going into your CPU, there are a whole bunch of cache, hierarchy of caches through which it goes, right? So the idea there is that when you're so the hierarchy of caches, for example, this is I forget, this is from I think Xeon or something. So the idea essentially is that you have your L3 cache. In this particular case, it's shared across all the cores of the processor, and then you have L2 cache and L1 cache, right? And so the idea here being you have hierarchy. So Okay, this is a good question maybe to ask everyone. So, why do we use this cache hierarchical caching mechanism? Yeah, I think some more solitons who already know keep quiet. I think I've asked you guys this question earlier. So why do we need this hierarchy of caching? Why is it helpful? To simulate the processing. Okay, what do you mean? Speed up. How does it speed up the processing? Okay. Why do we just directly access from memory? Why is cache? Why does cache take less cycles than memory from memory? It is residing in. So why is that any faster? Context switching, not exactly. Why is that? Why is that the case? Okay, so he's saying that your bus itself is not fast enough. That is one. Okay, so now, so I agree. Okay, memory. So in that case, RAM to this one you're saying is because of the fact that your bus is not fast enough. Okay, so then why do I need L3, L2, and L1? They are all on the same process, right? On the same die. Right? Addressing. What about addressing? So why does that have an impact? Why does the addressing have an impact on speed? If you have more, what happens? Exactly, right? Because if your addressing logic is too complicated already, which means that for each time you have to have that much of time, right? That is one reasoning. Another also is that the bigger your area of memory is, you still. I mean, yeah, your signal has to still flow from one point to other, right? So the larger area it covers also has an impact. Okay. So two things I know of. Maybe Uttara or someone can correct me. Any other reasons? Okay. So that is why So in some sense, this is natural, right? The more number of things you want to address, the more time it will take. Okay. So meaning, just to give a simple example, right? If I have a postman, he has to look up your address. Okay. If I'm always staying is in one lane and you have only 10 numbers, all you write on your postcard is 1 to 10, right? If you have 10 different lanes, on which you are staying, you have to say that lane 1 house number 1, lane 2 house number 2, right? Or if you have a JP Nagar or bigger area, then you need to have more and more things. So the more and more number of things, obviously your addressing logic becomes more complicated, right? And obviously the amount of area needed to be covered to do a query also potentially could increase, right? And again, you don't have your clock cycle. In one clock cycle you just do one operation. It doesn't matter whether it's short or long, right? Your clock cycles are in some sense designed to do this one. Is that correct though? That is how still all of this works, right? Okay. I'm verifying with our hardware team. So all right, so that is why we need cache, hierarchy of caches, right? Wherein L1 to L2 to L3, and therefore it ensures that we can have faster faster processing by having caches. So the whole idea is that you get a whole bunch of data here, and so this is much more readily accessible for the execution instruction and execution, which means that it can get data much quickly. So can anyone give me an idea of what are we talking about here? If I want to collect data from L1 cache, if I may have a L1 cache miss, how much cycles will that take? Approximately. What is that? Correct. If it misses L1, it has to go to L2, right? So if there's a L1 cache miss, how many cycles it would need before it can? Correct. Correct. To prefetch into the L1, how many cycles does it take? Much more than 3. No, from L2, correct. Assuming it's already then L2. Okay, you don't have a L2 cache miss, you only have L1 cache miss. So whatever you looked in L1 is not there, and you go and check in L2, it's there, and you get all of the data, and then you do your process, right? That's called the L1 cache miss. So if you have a L1 cache miss, how many cycles does it take? Approximately. It's about I think 200 or 300, 250 or so I think. It used to be at least that on Pentium. I don't know the current one how it is. Okay, so right. So essentially, as you go there, collect the data, fetch everything, and then start processing. So that does. So the L1 cache miss itself takes 250. The other one I think if I remember right, L2 something like 4,000. I don't remember. Oh, the number of cache. Yeah, I think that also it depends. Yes. Yeah. How many cycles? Yeah, 250 cycles. I also have to see. Yeah, exactly how it's calculated. What all parameters comes into the picture. Oh, L1. No? It depends. It varies from one to each of them. As small as 64 KB and as much as 256, even bigger. I think nowadays. I think I might have a slide here. No, I don't have a slide. I can tell you. I have some images here. I can tell you from that. Correct. The small L1 will be the smallest. L2 will be bigger. L3 will be even bigger, and your this one. Yeah, yeah. So this is usually about what? This is like 6 MB or so. I think this is usually like 250 KB, and this is maybe like 64 KB or so. Yeah, absolutely. And your many a time a processor with 6 MB cache will be much more expensive, okay, than a 2 MB cache, for example. What is that? This is a kind of architecture. There are few current ones where they are doing a lot more complicated things. Right? I mean, but they are very, very similar. Okay, the caching hierarchy and all are very similar. Just there are some slight differences between okay, which cache is, whether caches can talk to each other, etc. Okay, in some cases you have hyper, what is that called? Intel's architecture, the Nihalem, right? Which has got this quick connect, this thing. It's like I think it's like 18 Gbps connectivity or something. I forget. In between L2 caches, in between L2 caches. And how fast is now? Since we are at that, how fast is the memory to processor bandwidth? That I can say. One. Yeah, up to 1.6, 2.4 in the very best case. Yeah. Right? So 2.4 gigahertz. This one goes up to 20 gigahertz, okay, which is much faster to collect data. Gbps actually. Yes, that is correct. I have no idea. It could be, I don't know. Yeah. Potentially, yes. Faster, more expensive, yes. I'm almost sure they are, but I don't know if material is what makes it faster. Okay, so I'll keep moving. Okay, so now the case of two laws, right? So Moore's law is what we all has given us lot of speed up, right? So meaning doubling of components per integrated circuit every year. That's what it essentially says, and it has worked for quite a bit of time, right? But of late, especially from 2005, 2006 onwards, what has been noted is that there are what is called temperature hotspots on your processors. That is, small areas where temperature, it is miniaturized so much that the heat generated in very small region, the temperature density is very high. Okay, and I think at some point, some measurements that Intel did, I believe, it was I think 1/5 that of temperature density of sun. Okay, so it's like ridiculously hot at very small regions, and that essentially destroys the processors. Then if it goes to that temperature. So because of which we are hitting the power, what is called the power wall. Right? One is power itself, having a difficulty, but also heat being another one. So which means now, Moore's law is essentially, coming to a halt. Right? We are unable to, increase frequency by much. And there's a reason, I think, sometime back, maybe 1 year back or so, there was an article. I think it was from some government, US governmental agency, who did this study, and they were saying that by 2021, this is like a 2015 report. They were saying by 2021, we will not be able to do any more. Moore's law won't help us at all anymore. And I think just last year there was a MIT Tech Review article which says that Intel essentially is, they have put halt to Moore's law completely. Which they are no longer being able to increase the frequency of your process. And you probably already noticed, right? After 3 point, we all hit 3 gigahertz when 2006, 2007. No? After that, it's still 3 gigahertz, right? It's not become any more faster. Now people are all talking about more cores, right? And that whole reason is that is because of this particular thing. There are other things also, memory wall, ILP wall, etc. Meaning how fast can you get data to the processor, because just by processor being able to do is not enough. You cannot get data to it. Right? So there are other set of issues as well. But the heating is one of the major reasons why. So because of which now people always have been doing in order to speed up, one is to make one particular core as fast as you can, or to have many number of cores which you can do this. Right? And that is essentially what parallelism is. Right? This is optimization. I mean, not optimization, but this is essentially helping us do things faster. And the second one is telling about how much parallelism can we have. Right? And so the idea here is nothing but so if you have a problem that you want to parallelize, and you see that how much, if f is the fraction of the problem that can be parallelized, and s par is the speed up that you obtain for the parallelized fraction, then what you can do is your overall is nothing but the fraction that is not parallelizable plus the speed up that you get from the parallelized one gives you the overall speed up, right? So for example here let's say the case of if you have a 16 speed up you're getting and your the fraction you can parallelize is, let's say 0.9, okay, then your overall parallelism overall speed up obtained is about 6.4, right? So by doing this analysis we can know whether or given a particular algorithm and given how fast that particular small part alone can be parallelized and how fast it can be, then we can make a prediction on how fast the overall system would be and how much will it scale up if I add more number of cores. Right? Because we don't have a choice now, right? We are essentially stuck because we cannot increase the clock frequency, but we still would like to add more features, as we said earlier on, user friendliness, etc. So which means we have to get more performance, right? So then the question is about how do we parallelize effectively, right? Okay. So I think with this slide I will take a break. So now parallel architectures, right? So and many of these architectures, so examples of that are for example ARM11 has it's a 8-stage pipeline with up to 8 instructions in flight. I will say what these terms mean in the next coming slides. Just remember these numbers or the scale of these numbers, okay? So essentially what this means, the instructions in flight is how many instructions are in one of the units of your CPU, okay? We'll talk about them more in detail. The Pentium 4, for example, had a 31-stage pipeline superscalar. We'll say what pipeline is, what superscalar is, etc. in the coming slide. And up to 124 instructions in flight. And Skylake, for example, has quad core, 2 cores per thread, and GPU support as well. And now coming to some of the fastest supercomputers today, right? So, for example, this is I think from the latest top 500. So, top 500 is this benchmark where this is from University of Tennessee Knoxville and Oak Ridge National Laboratories in US. So what they do there is they see what are the fastest computers in the world. So what I mean fastest computer, it usually means fastest cluster computer, right? Or supercomputers as you call them. And so the fastest one currently is this Sunway Taihulit Light, I guess. So which is essentially a 41,000 core processor, 256 core from which is actually made in China. This is actually made by the Chinese. I forget the academy's name, one of their academies. So till recently it used to be one of the big CPU processor companies, but this one is I think is the first time probably it's another manufacturer. And that goes up to 125 petaflops. Any idea of how many flops our computers can do? You know what is flop? First of all, floating point operations. Okay, so instead of talking about integer operations, we talk about floating point operations. So how many flops can your computer do? Anyone? How GPU can go to? teraflops. Okay, that's a very high end ones. Your normal i7, how fast? Okay, about I think it's about 20 to 30 teraflops. Sorry, my bad. Gigaflops, my bad. I said teraflops. So yeah, 20 to 30 gigaflops. Okay, and how much did you say? This ones can do up to 1 teraflop, right, or 1 plus GPUs, right? So you see the fraction here, difference here, right? Okay, and these guys are doing petaflops. So what is petaflop? 1 petaflop? Is giga after tera or is something in between? Okay. Okay. Correct, right? So it's essentially this is 1000 times, right? This is another how many times more? What is that? What is 15? And that is again, for example, that's 125, right? So that is that much times 125 times 1000 times 50 times faster than your computer. That particular guy, okay? And the Tanhi, I think it's like a 32,000 Xeon processor with the 48,000 Xeon 5 processors. So these are again very specific processors. They are very similar to GPUs in some sense. This is what they called many core architectures. So the essential idea is that you have either you have full cores which are very powerful, very similar to your, somewhat similar to your Pentium architecture, or you can strip down the cores to make them very relatively lightweight. And one of the major activities is to do numerical computation very effectively. Okay? And so there could be add-on boards as well. So your normal operations are done by your normal processor, but these guys are for numerical number crunching, right? And similarly, there are these heterogeneous architectures. The one I told you about, the cell processor, the one during my masters I told you, right? We all worked on. So which essentially had what is called heterogeneous architecture. So all of these are homogeneous architecture. What it means is all of each core on the die is all of same type. Okay, so that's not necessary. So that particular one, they had a PowerPC architecture followed by 6 to 8 data processing units. Okay, so one is it's like a normal CPU with all the paraphernalia necessary to do other things. Whereas the other one, the separate cores, they are heterogeneous, so these are very different from each other, and these ones are only for number crunching, right, on the same die. So that is what people have been doing, and so this is where you are using a different this is again homogeneous as far as I know, but they all are for number crunching purposes. It's very much like your GPU. And that particular system, so this system actually is with that many Xeons with 5 processors, and then that gets I think 54 teraflops, 54 petaflops. So scale of how fast these things are. Now this doesn't really tell you how much can you utilize them. Okay? That's a different story altogether, which is about writing how well can you write algorithms. Okay? At this point, I think we'll take a break. Right?
Last question
Yes.
from the attendees. So, he's asking any recommendation for MOOC on this
Any recommendation?
courses? No, any recommendation on MOOC on this?
Oh, MOOCs for this. Huh? I don't know if there's a MOOC available for this, but I can suggest, I think his name is Vijay Nagarajan, right here. Vijay Nagarajan from Edinburgh. He has slides on his website, which is pretty helpful. I have to check up online whether there's any computer architecture course. And if you are, what is it called? Okay. Okay. So Harshit is saying there's one available from UT Austin. I think he will share that link on the group. So please join the group if you would like to get the links. Okay. Any other questions before we? Okay. We are breaking. In 10 minutes, so about 3:25 we'll start. All right. So shall we start? Okay. So till now, we said how if you want to improve the performance of an algorithm or of a particular implementation, what all can you do? The big picture we said, first and foremost, you can make algorithmic improvements. And algorithmic improvements, we said, there are two ways of doing it. One is optimizing the algorithm, wherein we try to come up with better algorithms, and we saw how big O notation can help us to give an idea of how better or worse an algorithm is. And then we also saw how we could potentially come up with parallel algorithms in order to do that. And we saw the example of matrix multiplication, which can be done parallelly. And was that example clear to everyone that how we did that blocks and the certain particular blocks were allocated to particular cores, and that is how we were doing it, right? And then finally it's all, each of them are done, the multiplications are done parallelly separately, and then we do the additions which are done separately again, all of which are then and which potentially could be done on separate cores. And then we spoke about how do you do that from architecture side of things. In that trend we spoke about what we spoke about the different kind of architectures and some intuitions of why the architecture today is the way it is. And we also spoke about the two laws, Moore's law and Amdahl's law, and then we also spoke about examples of parallel architectures in practice today, right? All right. So now let's come to the idea of parallelism. So as we said, we already spoke about how algorithmically we can achieve a particular algorithm, how we can know how much parallelism it's got. Now we have to map that parallelism onto the processor in order to really utilize what is there available in the processor in order for the whole system to be efficient and effective. Right? So to do that, there are two ways of going about it there. So one is in hardware side and another is in software side. Right? So in the hardware side of it, one kind of thing we can do is parallelism in uniprocessor. Now, which we'll talk about, which is one is pipelining, other is superscalar or very large instruction word, I think it's called, or long instruction word. I keep forget large or long. And the next idea is of examples like things like single instruction, multiple data, wherein you have single instruction, but you do like for example add, but you do that for multiple kinds of registers at the same time. Right? And the other way of doing that would be with multiple processors, so wherein either you could have multi-core or you could have symmetric shared memory processors, or you could even have distributed memory multiprocessor. Okay. And finally, you can have multi-computers. Right? That is, multiple computers, all talking over over Ethernet in order to do things effectively. And on the software side of it, you have instruction level parallelism, task level parallelism, data level parallelism, and transaction level parallelism. So the big picture here is instruction level parallelism is, I think I'll come to details next after this. So first and foremost, okay, so we spoke about already about the CPU and how memory is laid out, and here I'm showing examples of those. So as someone earlier asked me, how big can your caches be? So Intel's Barcelona, for example, I don't think anyone can see this. 64 kilobyte is the L1 cache. The L2 is 512 KB and L3 is 2 MB. And in Nehalem, it is L3 is 8 MB, L2 is 256, and L1 is 32 KB. So it really depends on your particular architecture and what all kind of what kind of sharing of memory also happens. Right? And this is what I was talking about, QP, the quick path interconnect, or QI, I think they call it, or QPI, I think. So, and I will come back to that. So that's just giving an idea of how these things are set up, right? Okay. So any of the modern day processor, you can think of the main processing that happens as consisting of 5 major things. So one is what is called instruction fetch. You want to fetch that particular instruction to be computed. Next is question. Next is instruction decode. So given a particular instruction, you need to figure out how do you to decode that particular instruction. And then you have to do the arithmetic or logic operation or the address computation, whatever that may be, the execution. And then there is a memory access or branch completion unit, and you also have the write back as well, right? So now let's say, for example, I have one instruction to be computed, right? What do? I give it here, then it goes here, then it comes here, then it does to the memory, and then finally the write back, right? So how many cycles does it take to do one instruction in that case? If I do this sequentially, 5 cycles, right? Is that clear? Okay. Now, can someone suggest how can you make it faster? Right. Okay. So the idea essentially is, the first instruction will be in the instruction fetch in first cycle. Second cycle, then we have, this is the first cycle, right? First cycle, where you are in one stage and you keep on, moving it, right? Is that clear? So this is what is called pipelining, okay? Where you are pipelining things, one after the other. Now, next is what is multi-issue superscalar, wherein you can issue the same, you can issue multiple. Essentially, you have multiple pipelines itself, which will allow you to do this effectively, right? So you could have, this is one pipeline, this is another pipeline, and both of them each of them can do one instruction per clock cycle, and so totally then you can, whatever, then you can compute that, right? Is that clear? What is that? Correct. So when you really look at your processor, right? What we are talking about is a simplified version of the same. So here, for example, I'm just giving you a big picture here, right? So this I think is a Pentium architecture or so. So wherein you can see here, this is the the integer processing unit. We have the floating processing unit, and similarly you have your other logics, right? Your instruction TLB, decoder, your trace caching, and bunch of other things, right? But the gist of it, you can think of them as modules, and each module doing various different activity, right? And that is how we are going back here. We are essentially simplifying and representing as this simpler diagram, right? Is that clear? So now coming back, okay, I have next slide here. So pipelining is nothing but, you are essentially, you also the example of pipelining, right? Superscalar was, where you have multiple pipelines at the same time to do the same processing. Can anyone say the difference between, what is the difference between superscalar and very long instruction word? Anybody? So one is done in hardware, the other is actually done at compiler time. Okay, the compiler learns and knows how to create the instruction in such a way that it will be effective. Okay. Now, so that is next, and SIMD you all already know about, right? How many of you know about SIMD? Okay, not everyone knows. Okay, so I will. So the idea essentially is, you are doing single, so it stands for single instruction, multiple data. So for example, if I want to do add A comma B, right, I can do, right? And it will essentially, oh sorry, I need to come to this side. Huh? So SIMD, let's say I want to do add A comma B, right? So actually it might do, if it's a simple operation, it might do, A register and B register, okay, and maybe let's say C also, maybe C comma A comma B. So you can have, this is your B and this is your C. So what does it do? Right? It will, do this, maybe this particular guy and this particular guy and save it to this guy. Okay, that's one way of doing it. So here instead what happens is you can apply this as a vector operation, okay, wherein you can say, oh, all the elements of A and of B, so you add this one to that guy and this one to that guy, this one to that guy, and copy into the corresponding C, right? So instead of doing a scalar addition operation, you do a vector operation. Okay, and that's why it's called a vector processor or SIMD. And GPUs also are somewhat working in the similar structure in some sense. What is that? It will be a different kind of instruction set. Yes. Right. So in this particular case, what happens is you are still doing. I mean, in one case, it is the same instruction you are doing multiple. I mean, for multiple different registers. In other case, it could be any kind of instructions. What is that? No, so I cannot do this. See, my add I am doing, I can only do with add. I can do 4 registers at a time. Right? The other guy maybe does in one cycle. It might do add a comma b and subtract d comma e, maybe in one cycle, because it has 2 pipelines. It can do that, and there's some extra bit things there. Essentially, you pack into it's a long word, and you pack into the long word, and then you operate on them. Essentially, that's what actually happens. That's what's called very long instruction word. But at the end of the day, it's not necessarily a one kind of operation. Okay. It could be 2 different kinds of operations. Okay.
SIMD also, compiler has to guide like how you have to kind of.
Correct. So compiler has to know whether it's a SIMD instruction can be generated or not. Yes, there is some intelligence needed. Correct. But the idea here being that it is one kind of instruction applied for many registers. Okay. And okay, so I think now can you switch to the other slide, the PDF. Now I'm going to steal some of the slides from Vijay, who's at Edinburgh, and use his slides instead of going through mine. So. Ready? Oh yeah, I also need to move it, right? Good to go? Okay. All right. So, so taxonomy of parallel computers. So the idea again here is being you can do single instruction, single data. This is standard uni processor. Single instruction, multiple data, which we spoke about. So usually it was it was used a lot for graphics processing, etc., where you would have to do graphics kind of shaders or any sort of those kind of operations. Then there is multiple instruction single data streams. This is rarely used in practice. And other one is the multiple instruction, multiple data streams. So where each processor uses its own data and execute its own program or part of it. And this is the most flexible approach and easier or cheaper to build by putting together off-shell classes. So, okay, and just 2 more things here. Is Guna somewhere here? No, he's there. Huh? Okay. Can you tell him maybe another 10 minutes I'll be ready? Okay. So there are 2 other in terms of the organization of processor and memory. There are 2 different I guess systems. One is called the uniform memory access model, and other is called the non-uniform memory access. So UMA or NUMA. So the idea essentially is that in one case you have a single memory unit which talks to each of them. Or so here, for example, all memories are located at the same distance from all processors, and it's also called symmetric multiprocessor (SMP). So many of your processors you will see the SMP, something called SMP written. Right? That's what it means, because it's it is the same kind of processors symmetrically assigned or aligned. Memory bandwidth is fixed and must accommodate all processors. So meaning this does not, which automatically means that it does not scale for a large number of processors, right? Meaning you have single bandwidth over which all of them are talking. Right? I mean, a single interconnection over which it's talking, so which means your bandwidth is limited. But it's used, most commonly for most multi-core systems today. The other one is where you have memory available for each process as well. So this is a single node where here, right? So memory is allocated with each processor, and accessing local memory is much faster than remote memory. If most access are to local memory, then overall memory bandwidth increases linearly with number of processors. So essentially, this allows you to do more scale up. Okay? So some of the recent architectures where they're trying to do larger scale up, they're using these kind of architectures. Right? You cannot do for more than, I think, 8 or 16 cores and all. You probably need different kind of access patterns. And also another thing is also, you can say your parallel computers based upon the architecture of your communication model as well. So what you mean by this is, you have different memory, but how is your memory shared? Do you share your address space, or do you have separate addressing for each of them, right? So one is the shared address or shared memory, in which case your process in different processors can use the same virtual address space, and any process can directly access memory in another processor node. Right. So for example, I can have variable A, which is then again used, that it is used in multiple different nodes as well. I'll show an example of this. It will be very clear. Communication done through the shared variables, and explicit synchronization with logs and critical sections. So, and it's much easier to program. Right. You don't have to do any extra complication. I'll show an example, then it will be obvious. So the other one is a message passing based one, wherein each of them have different virtual address space. And each of them have their own access to their own memory, and communication is done through explicit messages. You pass messages in order to do the communication, and therefore it's harder to program. And libraries you use are standard message passing libraries, MPI. So an example of that is for example here you have processor 1 and consumer, which is second processor. You can have flag A equal to 0, and there's some synchronization assuming, and A equal to then 10, and here you're doing X equal to A times Y, right? So even though they are on different processors or processors also, they are still sharing the memory space, and then because of which it's very easy for them to access that. Whereas if you're doing message passing, what you have to do is you do this A, and then you share that particular thing you want to share. You want to share with the other processor, and then you share that particular thing, and then you continue from there. Okay, so it's definitely much more harder to manage, right? So you have to explicitly share. Right. So yes. So the question is whether what is more important for you, right? Is the programmability more easy? Ability to easily program more important, or is it that this is more important for you, or is it reducing dependencies more important for you, right? Here you're making the dependency explicit, okay, which means that the programmer is taking care of that, right? But the side effect of that is the programmer has to very specifically say all this. There can be more complication, okay, because for example,
I can implement that with say atomic or something. First one and forget about it. Here I'm explicitly saying that
correct.
You have to
And
wait till it is being written.
correct. And you also have, exactly. So that is called, for example, if I have to send this message to this guy, I have to make sure that this is the one way I could do is I'm sending this message from here, and I have to make sure first of all it is written here before he is accessing it. So I have to make sure that one thing. The other thing is I might have this kind of messages, and I don't want to end up, let's say this guy is really on critical path, right? Where if I increase any time on him, it's going to improve my total time. So which means that when I'm sending the messages, it has to be in such a way that what's called double buffering. So you have to do communication and computation overlap in order to ensure that your critical path doesn't become any worse. So this means there are a lot more things than just you have to think when you're going to send the message, when the right time to send the message. So in order that he's not blocked at all. So a lot more complexity that the complexity is managed by the programmer, which is a side effect of that, right? But it gives you a lot more fine-grained access to what actually happens in the processor. Okay. Questions on that front before I go to the next one? Okay. Now types of parallelism application. So one is we said instruction level parallelism, which we already spoke of. Multiple instructions from same instruction stream can be executed concurrently, and generated and managed by hardware superscalar or by compiler, limited in practice by data and control dependencies. So the other kind of parallelism is thread level or task level, right? So wherein you can say that you know what, I don't worry about whether each instruction has so much of whether they are parallel, and I try to do so either I use superscalar or very large instruction word where I'm trying to do multiple instructions same time, right? Or in case of SIMD, here where what I'm doing is I'm saying I don't worry about that low level. I'm thinking at a much bigger picture, much bigger level. I only think about at the thread level, how I am separating the activities, right? So multiple threads or instruction sequences from same application can be executed concurrently and generated by compiler or user. So here we had either hardware or compiler, right? Whereas here it is the compiler or user who is managing that complexity, and generated by the compiler or user, but is managed by the compiler and hardware. And this is limited in practice by communication and synchronization overheads, right? So you have to make sure that your first thread completes before your second thread if your second thread needs your first thread's result, for example. Right? So those kind of things you need to manage. The next one is instruction same thing, single stream operate concurrently or temporarily or spatially on several data. So you have different data on which you are parallelizing over, right? And limited by non-regular data manipulation patterns or by memory bandwidth. So memory is another major thing that could be here. Right? So for example, if you have an image and you want to you divide up the image into different parts, so that is data level parallelism in some sense. Right? Each part you might give to a separate thing to do. But again, so it's not exactly the same because in most cases in that case you will probably use thread level parallelism. So not exactly one to one here. The other one is transaction level parallelism, which is what you're really doing is so multiple threads or processes. So imagine you have a major the particular software has got multiple different transactions it has to do. So each of those transactions themselves are parallelized as opposed to at so this is even higher at a bigger level than even at thread level. So where your multiple threads of process from different transactions can be executed concurrently. So it's from two different transactions you can have threads running parallelly, right? And sometimes not really considered as parallelism because you could it's that. And limited by access to data, metadata, or interconnection bandwidth. Now let's take a simple example. This is one reason why I want to show you these slides because it's quite nicely they have shown this example here. So let's say we want to do this particular operation, right? Which is I want to get the value here, which is nothing but 0.2 times all these these four things. Okay, so I sum up all of those things and then do 0 times that. Okay. How can we parallelize this particular thing? Any ideas? So don't read the bottom part. Assume it's not there. Okay. What is that? Make 4 copies. Okay. Sorry, I didn't get that one. Make 4 copies. Okay. Then what do you do? Shifted meaning? Okay. Okay. So what you're saying is make a copy of this guy and these guys, then move that by 1. Is that what you mean? M plus 2. So I have 1 copy, right? So let's say it's, my original one is 1 to n and 1
The next
to
one
n.
will be like 2
2
to
to,
circularly
okay,
2 to n plus n comma 0.
okay, uh-huh.
Like that, you can have 4 copies and then
Okay, you're saying, so then take the first one from,
so that n plus 1 cross n plus 1 will be n cross n will be
but I'm not so sure why that is giving you parallel, I mean, why that is important. I'm not sure I understood your, you want to draw that maybe?
reduced to some
So okay, you've shifted it, and then what do you do after that?
it's like shifted, placing it like behind each other, shifted and placed behind each other
Uh-huh.
and reduced.
Storage what he is saying that the 4 position.
Uh-huh.
So actually, create 4 copies of the matrix, shifted up, shifted left, right, down.
Uh-huh.
You just add them, multiplying by 0.2.
Oh, okay. But why would that be any better than taking the, I mean, just addressing them? Okay, uh-huh. Okay.
Two different locations, parallel.
And they are in different locations, but that's not necessarily helping us to improve parallelism, right? You see what I'm saying? Okay, take kernels, okay. Right, so what are the data dependency here? Let's think of that for a moment, right? What's the kind of data dependencies we have here? So, if I want to compute this guy, right, whom all does this guy depend on? Okay, all 4 neighbors, right? Okay. Now, if I want to update this guy, let's say, I'm starting a new cycle, okay, so I have all new set of values here, right? And if I want to update these guys, right, which ones do I need to look at in order to know, I mean, do I need to, can I use the, so I did one round, I have the values for this matrix, right? Now at this point for me, so this is our current matrix of interest, right? So here now to update this guy, okay, I have the previous values of all these guys already, right? At this point, what is my dependency like? Because what is that? Exactly, right? Up and left has to be updated before I can do this guy, right? Because these guys need not be updated, correct? And that is how our current algorithm itself is, right?
I also got initially.
Uh-huh.
You are taking the
Correct. The assumption. Correct. So yes. So I mean, essentially, what you're doing is we are doing a moving window, right? And then you are computing and you keep moving, right? Sorry, I made the assumption there. Okay, so I'm having a moving window and keeping on, updating it, right? Correct. Yes. Oh, so I should say that. So yeah, so the updates are in place. So top and left are new values, and bottom and right are old ones. So update occurs in multiple sweeps, and keep difference between old and new values, and stop when difference is small enough. So in a sense, what we are saying is, for this particular case, computing new value. So essentially, we can sort of move in this kind of a direction, right? If you want to effectively update them. So computing new value for a given point requires new value of the point directly above and to the left. So by transitivity, it requires all points. So okay, you understood that points there. So now the example of that with instruction level parallelism is something like this. So yeah, so we say, we state that diff, right? Diff equal to 0, and then we have 2 for loops for both the dimension, and then we say temp equal to a of I comma j, and then a of I of j equal to whatever that guy is, and then I keep the difference. You can just go to the code for a minute. Right. Right. I will show the other example now. I'm just giving you for the comparison sake. Okay. Now see the second case. So I'll show you one more. Just give me 1 second. Okay, you go through this and then I'll go to the next one. Where P is the processor number, capital P. Okay.
What is the PID?
Ha. Correct. P is the total number of processes and PID is the particular process. One. Correct. You are dividing it into blocks, right? And then you're doing updates, and then you're putting logs and barriers, right? So that you are making sure the consistency of data is happening. So this is where your memory is shared, right? Both of them have access to the same memory, but you just want to make sure that each part is done by each person, correct? And you just want to make sure that you're blocking them so that they don't cause problems, right? Clear? Questions? Now imagine the case where you didn't have even this. Imagine it's not shared memory, right? You have to pass messages, right? So whatever that the boundary values are, you have to pass them. Correct. You have to pass to each of them to make sure they are synchronized and everything else in order to make sure. So that obviously has a lot more complexity then, right? And that is what you want to avoid. And so here. That's the same as the last one, right? Yeah. Okay, so all right. I mean that's just to give an idea of that complexity involved there, right? Now, with that, yeah, I think we will show some examples. Guna, is he ready? Can you check? Yeah. So, so now the gist of it, what we're trying to say is, okay, now we know what kind of parallelism is available. We saw different kinds of parallelism available, both. So first thing we want to do is we want to make sure the algorithm itself has large enough parallelism so that we can utilize that by hardware. In hardware, we saw there are different kinds of parallelism that might exist, and each of them have their own trade-off, right? How do we share messages? Do we need to pass messages between each other, or do we need to make sure that there's some consistency mechanism we need to ensure, etc. So there are a whole bunch of things that programmers will have to do in order to ensure consistency. And further, we also saw that you can have some of those things already available by either through the compiler or the hardware, or in some cases the user has to come in to help ensure that. So in the software itself, you have to make sure that what you're doing can handle that. And so the real takeaway is this, that you have, when you are writing, when you want to speed up a problem, first of all do what we call a hotspot analysis, which is understand what your hotspots are, right? Understand what part is taking the most amount of time, right? And then ask the question whether you have one of the three, which is whether are you processing bound, meaning your number of computational cycles needed is much higher, or are you IO bound, meaning is it a problem with communication, IO not being found in time, or are you memory bound, right? Because you do not have enough amount of memory. So figure that out first, and once you know what your hotspot is, let's say if it is processor or processing, in that case then go and address that particular thing, right? And then you say, oh, what kind of parallelism or optimization can I do, right? And it could be algorithmic. So in general, as we have seen already, we said that our speedups can only be linear, right? Whereas algorithms we saw need not be linear improvements. It could be much better also potentially, right? Now, at the same time, coming up with an algorithmic improvement that is more than linear might not be very trivial. It might, some things take, so for example, matrix multiplication for going from 2.8 to 2.3 took, I think, 10 years or so, right? So, or maybe even more, 20 or 30 years, right? So you can, yes, it might give you good performance, but you don't know how much time it might take you, right? It might be something very trivial to do that you're just is just within your reach, or it might be something off completely. So do some back of the envelope calculation to see what what you could get from each of them and give it some shot. Now next is obviously you can use hardware. In hardware, as we said, you have different different ways of doing it. One is see whether your code itself is optimized or not. If it's already optimized, then one thing you can do is try to parallelize it. And parallelism, we said different kinds of parallelism. Right? First and foremost, see if you can have transaction level parallelism, which is to do different things of different activities parallelly, which is the easiest to do potentially. If that's not enough for you, you need further performance. Go to thread level parallelism, then see how you can do that. And finally, you go down to lower level like instruction level or anything else. Right? But now coming up with so the one of the things you want to do is a good library is that it should automatically do a lot of these things for you, right? You should not have to worry about a lot of these things. And TensorFlow does some of these things for you automatically, right? Now maybe one or two things I just talk about before wrapping up is this that so there were two or three different paradigms before TensorFlow, right? One is like MapReduce, right? Where the idea essentially is that you have the way the parallelism works is something like this. You have like you have barriers, and you have some computes, and you do this computation, and then you want to turn this here. You do the computation here. Each compute, and then you do some fusion of all those values, collect all of them, and then again you split them up, and so on and so forth. But the assumption here is that this task and this task are of this nearly similar size. Right? If they're not a similar size, then you're screwed. Right? If this one takes let's say 1 millisecond and this takes 100 seconds, okay, there's no other way of splitting it, then you're essentially screwed. Right? So this paradigm only works under the assumption that all these ones have same amount of critical path for that period of time. Right? So that's the first question you need to ask. Will my using this with MapReduce, will that really solve my problem? Right? Many a time what you'll see is people just tend to use whatever paradigm, whatever they know, as opposed to theoretically or systematically going about and saying what will really work here or not. And in between, then there were other ones like I think Manjunath will talk about, I believe, Giraffe or Preagle, which are slightly more sophisticated than these ones. And then you had other kind of ideas in machine learning, which is parameter servers, where you have different parameters over which you want to optimize, and you send those parameters to the architectures to optimize them. Okay? Now the way TensorFlow does this, is what they call computational graphs, which I think I will let Manjunath speak about, and how they smartly do all of this. Right? So a good library should ideally know how to split the tasks such a way that each of them can do their activity very efficiently, and it should work across multiple, any multi-core architectures, right? That will be nice to have, right? Whether it's my normal computer or my GPU or whatever it is, it should automatically apply. It should not be very specific to a particular processor, right? So if you go and do instruction level optimization, it probably might not be a good idea, right? Because it might be very fixed to that particular architecture. Whereas if you have an algorithm that automatically do some of these kind of things, that from a big picture start decomposing them and splitting them up, that probably is much more effective. And so yeah, so that is it's coming. What is that? Tell me it's okay. You can just show that without running it. Okay. So just show one example of code vectorization. Questions at this point? So can I ask another question in that case to you all? So let's say I have a task t I want to do, and I divide them into I have a task t, and I divide them into now, I mean, this is, it's an amazing task, okay, that I can split it up into any number of pieces I want to, okay. So I can make it as small as, into say 100 pieces, or I can make it even 1,000 pieces, right. Now, and let's say I have, 10 cores, right, and I'm running this, is there any advantage of doing, so is the problem understood first of all? I can either split it into 100 pieces or 1,000 pieces, okay. And then each piece, then I can keep on greedily giving it to my system to compute, right? And each time I'll call a thread, I'll assign that activity, thread will do it and come back to me, right? And then I finally can fuse all of them together, right? So is there any advantage of doing T100 over T1000? So there's no dependency, right? All I do is just split it up and then just fuse them, and that's all I'm doing. That's like a O of 1 operation. Right. You could potentially have thread overheads, right? So you need to worry about those kind of things as well, right? When you are implementing them. So this actually, the reason I was asking this is one of the first things we did, and we were optimizing. At one point, we just spawned a large number of threads, and then we're like, it's going slower, and then the bulb clicked, oh, you know what, the thread of the cost is there. So that's an example of something. So there are a lot of other things you have to worry about. It's nice to do these things to optimize them very well, but there are other things you have to worry about when you are implementing in general. Any other questions? You could do that, but again, the thing is, see, I mean, who's going to manage the complexity? Right?
Management is not with us. You don't know how it can execute, it can be faster or slower.
Sorry, what is your question? I didn't quite.
No, you do threads inside threads. Since management is out, like with the processor and hardware level, whatever has been written, it is generally not a good idea because it can be stopped at any time by the processor if it clicks.
Right. I mean, so it's not just that. I mean, you're.
Data dependency is the major problem. Because threads inside threads doesn't matter for the processor. It will again execute them sequentially.
So just by doing recursively calling, I mean, having threads not necessarily solves your problem.
The processor is, I don't know about what is managing it. The processor can see that it need not allocate resources. Those kind of things also happen by having it inside.
It's linear only.
Or it will be decomposed to linear as you are saying.
I mean, so at the end of the day, instructions will be, it will just be, yeah, correct. I mean, see, that is the abstraction you are creating, right? This is the question I ask a lot of people, right? So why do you need, the question I ask them is, why do you need OOPS programming language, right? Why do you need OOPS programming language? I mean, any kind of OOPS language.
It gives a better modeling.
Yeah, why do we need that?
I mean, for me personally, it is like managing things becomes much more easier.
Exactly. The important part is not, the computer doesn't care, right? It's for humans. It's for human readability that we are doing all this, okay? Because many a time there is the assumption that your OOPS or anything, whatever it is for the computer. Computer does not care. It's just doing one instruction after the other. It really, yes, it's actually you're making it harder for the computer, right? So essentially, why you're having all of that is so that the humans who are reading it can make sense of it much easily, right? The same thing here, right? Whether it's recursive or this one, the computer is doing it in one way. It does not really care. Now, at the same time, there's a subtle question there that you're asking, which is, it will become harder for it to make predictions. Okay, if there is some very complicated prediction mechanism, it will be harder for it to do certain things. That is sort of true. And in general, people don't call threads within threads and all because you are unnecessarily getting more and more overheads, right?
I do it actually, but it doesn't give any sense.
Yeah, it doesn't.
If your data is dependent on previous data or something.
I mean, why would you want to call thread upon thread, right? Oh, you're saying because of to have a recursive structure, huh? Okay.
It depends on
Discussion structure or managing becomes easier for me.
Right, so you don't need, I mean, what I'm saying is you don't need a thread for that, right? You could have one function calling another function calling another function, you're recursively calling things, right? It doesn't necessarily have to be a separate thread, right? Your thread is just for, it is in some sense a unit of, a conglomerated unit of work, right? And for a particular part of a processor or someone to do that activity, right? So why do you have to have that extra? So essentially, I mean, you have a process, right? That is one single activity, and inside which you have a set of threads, right? So it's a level of detailed, I guess. So it's not as general as a process, but slightly at a slightly lower level, but it's much bigger than a function, for example, right? So this has overheads, right? This is only useful if you want to do certain things in certain, you want to essentially affect certain things. Meaning, for example, I want to have this particular thread running on, I want to latch it to a particular core or whatever it may be. Those kind of purposes why you have a thread. Right? You don't need a thread if I just want to call function after function. Right? I just need a function. I can have a recursive function alone. Does that?
Where even within a thread you want to do some IO operations separately.
Right.
Where you want to start another thread.
Correct. Yeah. Sure. I mean, so yeah.
Management
Correct.
becomes easier for you, but
That is, yes. So there are lightweight threads also which you can use for such cases. But there could potentially be other issues. Anything else? Any questions?
If you are able to solve that,
Any other questions? You want to add something? Okay, Guna? Is it running now? Hmm? Okay, sure. Whichever one you show. Here's the mic. You just tell me.
Hi. So as Sumod speaking about, right? So the kind of parallelism and things like that. So SVM we all know, right? So this is. So just an example to tell like single instruction and single data and single instruction multiple data, right? So how much difference can we get when we actually implement the code, right? So just a simple example. So this is using a single for loop to iterate over the number of samples that we have in the data. So I am just calculating with one loop. So if you see, I am getting around 7.45 seconds. The same one with SIMD. So it takes only 1 second.
If you don't present it, don't run.
Sorry. Okay. So this is removing a single for loop. We are able to get like 7%. I mean 7 times more performance, right? If you see in the code, we haven't done. Nothing great like. So it's a single for loop here to iterate a number of training samples. But if you come here, I just did everything in a matrix form. So and a vector form, yeah. So this just an example, right? When we write code.
Can you go to the
Okay. So W weight matrix. So X my input training data. Y the corresponding labels for that. So number of classes is in shape 0. and then so the first for loop is to iterate over the number of samples, and then I compute the scores, and then if you see the SVM loss, it's like so this is the loss for a single sample, like so max of 0 comma correct class scores minus correct class scores plus delta, the margin that we had, right? So that's what I have done here. So if it's same class, so I just skip it. If it's different, then I compute the margin, and then I'll add the margin to the loss. And so this particular thing is I'm updating the gradient for that. So I'm iterating through all my training samples. The same thing here. I'm just getting the entire training samples in X, and then computing the score with direct vector operation w.dx. So and then little bit of NumPy tricks to compute the loss. So with a single for loop and little bit of matrix manipulation and vectorization, we are able to get like 7 times faster performance. So when we write code, we should be thinking in this way to write, so that we can use the SMD that is available in our processor.
So I mean, the gist of it is that when you are writing code, even in Python for that matter, you're making it a vector operation and keeping them as vectors. Then the compiler can actually convert it into SIMD instructions. But if you write it as for loops, which is not vectorizable, then obviously you'll get a performance hit. So what's really important to remember is that keep things as vectors and vectorize your code. That way it becomes a lot more easier for the compilers to create the vectorized code as well, SIMD code as well. Okay. Yes.
Is it not the case that some amount of looping that actually occurs in C, looping in C is faster?
Uh-huh.
Is the improvement not due to the fact that lot of looping is occurring in C and not in Python?
No, in both the case it's the same, right? Why would that make a difference?
Because you are giving chance to compilers that can understand and convert into a better code, optimized code, which is making use of SI.
So I mean, see, for loop in Python or C, it won't have a big difference, right? And yes, I mean, so what you're saying is correct. Okay, but what happens many a time is that, I mean, that could be part of the reason. Okay, but in this particular case, I mean, it's quite likely that this is what is happening. Okay. No, so what he's saying is that because you have a for loop in Python, which in later case is not there, the equivalent implemented in C would actually be having a for loop, and that is why he is saying, in one case Python had a for loop, in other case the for loop is in C, and is that the reason why? But I don't think in this particular case that is the big difference. Got it. I don't know how much is contributed by SIMD particularly in the specific case, but in general, you do see that difference. So in general, whenever you write code, the takeaway here is that do write it such a way that it can be vectorized.
Depend on the data structures that you are using within the loop, not just on the loop. If you are just using the multiplication, I think the C versus Python code will not have any difference in performance. But if you are using complex data structures, that will make the difference.
So adding to what you were saying, right? So yeah, looping in Python is slower, but when I do the looping, right? So the compiler will just do, it gets converted only looping code, right? It doesn't do any other things, right? But when I do NumPy, internally their code is actually SIMD. So the other management things will be done, but the instruction will be SIMD. So when I do the first for loop, right, it can't use that SIMD instructions because you are saying I want to go through one by one, right? You are restricting it, right? But when you do it NumPy arrays, so NumPy array internally, if they find that processor can use it as SIMD instructions, then that instruction will be used. So that's why it's faster.
Right, but the thing is, when you write a for loop, the compiler has to be smart enough to understand this for loop actually can be simplified or it can be avoided. But that, usually compilers are not that smart. Correct, yeah. OpenMP?
OpenMP,
Correct. Yes, I mean, so the vertical case what you're trying to say is that the for loop, the compiler has to be so smart in order to know that this for loop actually can be vectorized and there's no dependency at all here. Got it. I mean, ideally, yes, if your compiler is smart enough, it should be able to, given a code, it should be able to create vectorized code for it. Right? Completely vectorized code, right? But the complexity of that is so big that we cannot have compilers that smart. So current level of this thing, they are unable to do that, which is why we are doing these things. And actually, some of these things will be spoken about when Manjunath talks about. They do some intelligence there. They make their one of the things they do is something called XLA, which is this particular compilation for TensorFlow. So I don't know if they'll talk about it, but I think he might. Right. So it depends on the architecture. Whether the architecture provides that. So they are usually there in DSP process, for example. Your DSPs usually are the ones which have that. You don't. So not all architectures have all kind of parallelism. Right?
So those family of processor supports VLIW.
Any other? Right. Right. Correct. Using those instructions. So I mean, ideally, how you would write it is you will go at the lower level and write them as SIMD instructions. It will be like SIMD add or whatever instead of normal add, right? Or you can do parallel for example, instead of for. But what you can do, I mean, if you have a smart enough compiler, in many cases you have, which automatically generate the SIMD also in that case.
So when they write such codes, they will have so many as defined internally. So when they are compiling to that architecture, they will go and find what are all the instructions that this particular process supports. If it's supported, then they will compile with that. So that's how most of them write.
All right, I think then we are done for today. Thank you all.